So this will be a kick-starting session of integrating AI with quantum computing. All right. So we have received like 50 plus registration, right from students to corporates to UG, PG, PhD students, and also different professors. So I'll try to have my session blending to everyone. All right. During the session, if you have doubts, you can ask questions. You can click raise hands, and then I may call your name. It's time now. Hope you're able to see my screen, professors and the participants. Uh, Thank you for joining. If you could have your cameras on, it will be well and good. Thank you, uh, scientist Krishna Swami RSS sir, for joining us from US. And we have different professors and students. They are joining. Joining. All right. Um, Let me begin the session, and as they join, let us see to it. So, welcome you all back, and I'm Dr. Doreen Robin, the founder director of CIRF. CIRF stands for Computational Intelligence Research Foundation, and this webinar is about how AI meets quantum computing. Like kickstarting from 2026, we have been working with a lot of algorithms with AI. So, for example, machine learning, deep learning, and generative algorithms. And as we start finding solutions to problem, the problem is becoming more complex. So the next for the decade, it's going to be AI, how it meets quantum computing. And this session, I'm going to focus more on the research pathways, right? What are the different research pathways on integrating these two technology? What are the different tools? I'll be sharing some of the tools, some demonstration of these tools, and what is the opportunity for the next decade, right? From classical computing that we work on with, and how we are integrating to quantum computing. One question I'm going to ask, I want you to respond just in one letter, Y or N. Y stands for yes, N stands for no. How many of you have worked with quantum computing? How many of you have worked with quantum computing? I want just one answer. Thank you. Just to know the recipients whether you're new or you've already been working on with that. I've got responses from two others. Quick, please. Have you worked with quantum computing? Yes or no? Yeah. Most of you said you're not working. So I could understand it's a new uh, domain that you're working with, because we have different people working with different technologies. All right. So before we start with my session, all right, I will be showing you a picture that contains the letters, right? Say, for example, it will have colors, but you should not read the color, you should not read the word, you need to read the color of the word. At the end of, I'll be giving you 20 seconds, I repeat it. You need to read the color of the word, but not the word. From the first to last and last to first, and 20 seconds will be given to you. Let me see how many of you are completing it, and post which you can share your experience on the chat. Shall we? Here we go. You need to read the color of the word, but not the word. From first to last and last to first. Yes. Now done. How many of you have completed or not completed? What is an experience? I don't want whether you have completed or not completed. What is their experience? Just put on the chat quick. Or you can unmute and speak. We played a very small game for just 20 seconds. It was confusing. Thank you. Thank you, Professor. Why? Because not completed. Thank you. Others. I don't know how many of you really played the game. All right. I could read YBR. All right. Thank you. All right. So you could, because it was like you need to read the color of the bird, but not the bird. Some of you couldn't complete. And I have played this game to my thousands of sessions that I had. Like one solution, like one person he gave is that he just focused on the colors but not the word. He said green, green, three greens, three reds, and four blues, and he was able to complete it. The way we approach the problem is very different, but we were not able to. Mentally we should be strong enough to read, and I've completed. Thank you, Bhavna. All right. And there are different methodologies. See, some of you used different methodologies to solve this certain problem, but the timing was such a challenge, right? And like Professor Raghavan said, it was confusing. Like as we build algorithms using AI, this quantum computing today, we are going to see how this is going to fit on. And one of the powerful factor is that it helps us to solve problems with quicker way, and helps to work more on with better optimizations. All right. And let me have my next picture. I'll give you 10 seconds. You need to find what is the mistake on this picture. Either you can put your answers on chat, or you can unmute your mic and speak. Here we go. Yeah, now it's time. 10 seconds gone. Whether anybody you're able to find what's the mistakes on this picture, please? No water on the other side. Well done, Professor. See, sometimes we are focusing on different versions of it, right? We are finding what is the mistake here, there, but naturally, you see, the river is not flowing on the other side of the picture. As I highlighted here, you can find it out. This is how we have got different problems, and we use technologies to find solutions to these problems, right? To find solution to these problems. So when we start, what if, my question to start my session is, what if that take today's supercomputers, thousands of years could be solved in minutes, that which could be solved in minutes? What if AI could learn, reason, and optimize beyond classical limits? All right. So some processing takes a larger time, and some processing takes a shorter time. Right. When some we work on a critical environment where we need to find solution at the minimal time. All right. So that's the question to start off with the session, right? If it is going to be thousands of years, even if you get the result, it is not going to be on time. All right. So there and where we are going to work with quantum computing, taking from the participants other than researcher Krishna Swami sir and others. Most of you said you're new to this. All right. So it's a new paradigm of computations, right? Here in quantum computing, what are the basic or the major four principles that you're going to use? It's qubits, right? We say quantum bits or qubits. How many classical bits we have? Either zeros or ones, right? In classical computing, either you have zeros and ones. In quantum bits, it can take different, it can take both zeros and ones, and as we journey through, you'll be seeing to it. And the next position, the next principle is superposition, multiple state at once. right? It can take multiple slate at once. That will be working. This is one of the interesting principle that helps. And also I'll be showing you the comparison between the classical computing and quantum computing. Entanglement. I hope most of you would have worked with the AI. I know most of your answer would be well, yes, right? How many of you worked with heat maps? Right? How many of you work with heat maps? What is the basic principle behind heat maps? Answers on chat, please. Or you can unmute. All right. Yes. What is the basic principle behind heat maps? Heat maps in general, it works with a correlation, right? It works the correlation between the different features and the target. All right. And here we see basically when you're going to say, for example, if you're going to use seaborn, by default it uses, if I'm going to give a data set and try to find generate a heat map, at the behind the principle, the strong principles, the correlation between the features, right, and the target. Self correlation. How many of you like yourself? Every one of us, we like ourselves, right? So self correlation is always 100%. And how do we like with other members, right? Maybe the workplace or in the family place, some of them we like more, then it's a positive correlation. If you don't like, then it goes to the negative correlation. So basically, in machine learning, deep learning, when we work with heat maps, listen carefully, therein we use in general default it's Pearson's correlation. You can also use Manhattan correlation or Spearman correlation. All right, there you need to specify explicitly. But there it works with the distance. But here, the best part of quantum computing, regardless of the distance, because the bits can take positions between zeros and ones on superpositions, right? So you don't have a static state. So where an entanglement has instant correlation across qubits, regardless of the distance. So this helps us to converge the problem, helps to solve complex problem at a faster time. All right. And quantum interference and amplifying the correct outcomes, right? And this allows to work process exponentially. Otherwise, in classical problems we work linearly. Here you work exponentially when you integrate quantum computing with your AI. All right. So this is how you can see the qubits can take any positions. In classical, you have either zeros and ones. Here you can see the number of bits is 5. Can you see throughout? So that's what we call it as quantum bits. So in classical computing, you take bits between zeros and ones. In qubits, it can take different positions, both zeros and ones at the same time, right? Here you see operation of quantum bits, 0 and 1 at the same time. That's what this principle is called, the superposition. All right. Qubits can take same value simultaneously, which helps into more of parallelism. All right. So here we say zeros and ones. Here 0 plus 1 at the same time. The superposition, I said, or you, the second principle is about entanglement. Regardless of the distance, it can do the correlation, and that helps to find solutions to many problems. What are the critical milestones on quantum AI? They're less error prone and more powerful quantum system. That's the first milestone. Second, today's session, we are going to see about different open source modelings and the training frameworks and substantial and skilled developers in the ecosystem. All right. And compiling AI application for which quantum outperforms classical computing. All right. And I don't know how many of you have seen this. I can give this on even on chat. All right. Quantumai.google. Anybody you have seen this? Have you visited this website? I'll give you a minute. I'll also put it on the chat so that it'll be easy for you. All right. This is Google's Quantum AI. All right. And in today's session from this environment, I'll be using a package and showing you a demonstration as we work through. All right. You can see to it, our mission is to build quantum computing for otherwise we call unsolved problems, right? You would have worked with NP hard, NP complete problems. Yes. And this quantum integrating this with AI It's not a replacement. When it is integrated, it's more efficient and less, it takes less time to find solutions to the problem. All right. Verifiable quantum advantages in real world application, you can see through it. Quantum ecos. All right. And there are papers, there are videos. So it's this. All right, as we find time, it's on, you can find it out, right? And there are different papers available, and what are the different milestones. So they've come to error correction, and you can see what are the different milestones to achieve it, right? So the error correction, it is working at a very large state, right? So this is about the environment. I would just want you to know how, what are the resources they provide, right, you, for you to simulate. And there is a lot of research opportunities available. All right, even if you are a PhD scholar or a first year student or a second year student, and so much and so more, right? Like jumping back to our slides. So you know what is artificial intelligence, right? Most of you, if I ask you a question, have you worked with AI? I know the entire answer will be yes. All right, the entire answer will be yes. And here it learns from data, right? So AI is the bigger umbrella word. The subset of AI is machine learning. The subset of machine learning is deep learning. The subset of deep learning is generative AI. All right, but what by and large it does, it learns from data, all right, and it identifies the patterns and makes prediction and decisions and optimizes. This is where we work on. This optimization is more powerful when it is integrated with, when it is integrated with quantum computing. All right. Say for example, you, when you use YouTube videos, it shows you different other videos that is training of the same type. All right. What runs behind is AI. I'm telling the general word AI. I'm not making it specific. And if you're opening Amazon to buy some product, do you buy products in Amazon? Or Amazon or Flipkart or whatever it is. You always see customer who viewed this product has also viewed the other product. All right. And medical diagnostics, whether there is a disease, yes or no. All right. Fraud detection, even in banking sectors. All right. Autonomous vehicle. Say very simple example I always say, when we go into our school life or college life or work life, first day we speak with many people. As we spend time in the workplace or in college, right, after maybe 6 months or 1 year, we'll be learning from different people. And then after sometimes we find for us this person will be adaptable, trying to learn the behavioral patterns. If you like the behavioral patterns, then we develop a friendship with them. All right. It's not always the first who met is our friend till the last of your, maybe at your workplace or your college. Yes or no? So learning from data, and you make predictions and you make decisions. When somebody comes to your, suppose your friend comes to your office or to your college, and he or she is dull, by seeing a face after a few months of having a good friendship with them, you'll be, even without they open their mouth and speak, you can ask them, is there any problem, or you sad, right? So like that, as humans we process data. First we learn from the data, we identify the patterns, and then we make predictions and decisions. But we cannot work with huge volumes of data, but rather in AI you can work with huge volumes of data. And even to make it more faster is where the integration of AI and quantum works. All right. Whether you're able to understand till now, if you're able to understand till now, type Y on the chat. If there is any doubt, you can put D on the chat. I don't know, I'm very fast. Yeah, thank you, Professor. Thank you. I'm getting response from three people. All right. Others? Any doubts? All right. All right. So thank you so much. So quantum, it works with qubits and superposition. Entanglement, I said it works, correlates very faster regardless of the distance. Right? Say for example, if you use k-neighbor algorithm, it works with distance, like Manhattan distance or any distance, Euclidean distance, and the quantum interference. In AI, it learning from patterns, pattern recognition, prediction, decisions, and optimization. When we integrate, there's a perfect synergy that happens over here. All right, it's massive parallelism. Right, I said zeros and ones. In classical computing, it takes either zero or one. Here it can take zero and one throughout the sphere. All right, complex state spaces and probabilistic outputs. Right, it works with probabilistic output, and that's some of the greatest takeaway of integrating with that. And we say AI is getting outdated. Once it is integrated to quantum computing, you will be able to find good solutions to problems, right? And I'm happy to see there are students from first years have also registered. So you have a good journey. Try to learn this technology, and you'll be able to solve problems even better than others. All right, and uh, comparing between this classical bits is what we generally use in computers as zeros and ones, right? It can exist superposition, zeros and ones at the same time. Here it works linearly, right? Here it works linearly, rather here it is exponential due to the parallelism. And then here it operates independently. Here qubits can be entangled. This is the greatest takeaway, showing non-local correlation, right? Correlation. And here it's directly observed. Here it collapses the qubits to, I'll show you a demonstration of both with IBM's and then also with Google Quantum AI. All right, with the package. Yeah, it's very relatively stable and easy to correct because it's only two stages, right? Here, very high sensitive to noise, difficult to stabilize. All right, when you take the computational advantage, it's effective for classical problems. It's very powerful for complex optimization and simulation, right? Now there is a lot of simulation that's going on. All right, because the problems are getting more complex, and there is a greater challenge in the optimization algorithms, right? Some of you would have worked with particle swarm optimization algorithm and colony optimization algorithm, artificial bee colony optimization, the different optimization algorithm. But sometimes it takes time to converge onto the space to find the solutions, right? And that's output. But when integrating with quantum, it gives very, very powerful optimizations, right? So AI with quantums is a powerful quantum algorithms with machine learning to solve problems where the classical computers cannot be used, right? And especially in drug discovery, the intensity of different diseases are changing every day, and for drug finance and fintech, right? Fintech, how the trading market goes on with, and on integrating that, and many tools that are going to come up from year more with quantum, with the AI on financial and material science. How much different materials also in quantum can works with quantum chemistry, right? The how much heat is given, how much heat could be resistant and quickly to simulate it works, right? And why AI helps to manage complex systems and error corrections. So where we find quantum accelerators AI, and AI refines quantum hardware. This very greatest takeaway: quantum accelerates AI, and AI refines quantum hardware. All right, it's both give and take policy, and on combination is going to be a greater synergy that is coming up, finding solutions to problem converging at a very faster rate. All right, what are the different use cases that quantum computing uses is on artificial intelligence and machine learning, finding solutions to different problems, and also with cryptography and data security, right? You would have worked with different keys. All right, drug discovery is something very important that many people have started working on. If you're going to kickstart your research, this is one of the best domain I could say that you can start off with. I will show you a paper that recently they have worked on with, and risk predictions, right? You would have worked with different risk predictions and classification algorithms, maybe in machine learning or deep learning or integrating with quantum. It is going to be a different shift on your results, right? Finance modeling and portfolio optimization, and this is also going to be a greater start right from 2026. Traffic optimization and smart cities, weather forecasting and climate modeling. Even at CIRF, we have worked with researchers who work with cyclone tracking. right, on traditional machine learning and deep learning algorithms. And now you find if it is going to be integrated with quantum computing, it is going to be even more better. Grid optimization, power grid, material science and designs, protein foldings, right? Quantum chemistry is something that different packages, libraries that Python also gives. Design optimization, quantum in space, right, in space computing, and also supply chain and inventory optimizations. So this already said it takes only zeros and ones. It takes represents either zeros and ones. It's exponential, and here it's linear. All right. There's higher error rate and need to be ultra cold. It has lower error rate and can operate at room temperature. This is one of the thing that we have to see very carefully. Well suited for optimization problems and data analysis and simulation. This can be handled for classical computers. So these are different applications of quantum, for AI, for better batteries, for cleaner fertilization, cyber security. Cyber security something is going exponentially. The threats, right? The drug development, electronic material discovery, financial modeling, solar capture. This already I said, traffic optimization and weather forecasting and climate change. For example, if I take drug discovery, AI can analyze millions of possible drug molecules, right? And it requires enormous power and time. Often gets stuck with local optimum solution. But when integrated with AI, you have a promising molecular structure. It evaluates the molecular energy state simultaneously with quantum simulation, and AI learns from quantum results and refines the predictions, right? So I'll show you how quantum AI is accelerating the machine learning, whatever the. How many of you have worked with machine learning or deep learning algorithms or generative AI? Any algorithm you have worked? You can just type Y on the chat. If you have worked, if you have not worked, you can type N on the chat. I want everybody to answer, please. Okay. All right. Listen to this video, please. All right. So you're able to understand, right? How fast, how well, there's a greater need of it, right? So enabling breakthroughs in healthcare, cybersecurity, finance, and climatic model. So if you're doing research, you can focus on these areas. So you can make a note of it if you want to. All right. And it opens new research and publication opportunities. All right. Does not require scale quantum hardware today. There are different simulators available. If you're a PhD for research, or if you're working with any funded projects, you're working with different universities, and it's also interdisciplinary. All right, it is also interdisciplinary. Why this topic now, right? We have, what are the problems that we have with classical AI, right? AI has achieved remarkable success that, there are when you go into the research publication, you can see millions of papers, millions of researchers are working with. But what is the problem? But this progress comes with very serious limitations: increasing data, exponential compute cost. That's one thing, because the data, when I'm doing my streaming now, how much bits have been transferred, right? How many bits have been received, how many bits are uploaded, or energy consumptions of larger models. And optimization is something very, very important limitations that we have. Millions of molecular combined to evaluate, like you have to search a vast key space securely. And climatic model, climatic is changing the entire world. It's not always the same. All right. with many interacting variables. So I've got different variables. If you take the geospatial data, the data are something so much and so more. And also, how many of you use ChatGPT or Gemini or Cloud or whatever I call as GPT models, right? Training requires thousands of GPUs weekly on monthly. I know nowadays when we work with people, people are not even going to Google to search anything they want directly. They jump into any of your GPTs, right? Massive power consumption. So why this leads to quantum thinking? Because AI informations are processed sequentially or in parallel but deterministically, which limits its ability. That's very, very important to explore massive solution space. Why AI needs quantum? That's the next question. Because the future space, because data dimension, when you work with two-dimension data, three-dimension data, four-dimension data, five-dimension data, or on a space that you want to work on with, the data dimension goes faster than classical models. All right. And NP hard optimization. Many AI request searching a huge solution space. When your problem is of NP hard type, I tell you, finding a solution with normal traditional AI is very challenging. All right, and longer conversion time. So because of the entanglement feature that is available in quantum, on integrating quantum with AI, the conversion times is very short, even for complex problems like npr problems, right? So training takes many iterations to reach good accuracy, but with lesser iterations and with lesser time you can get the same accuracy on integrating quantum with the AI algorithms, right? So here you have higher dimension. Some of you would have worked with principal component analysis (PCA), right? Where we reduce the higher dimension data into lower dimensions of data. Qubits naturally they present complex feature spaces. All right, and faster optimization happens here. Quantum algorithms explore many solutions at once and improve pattern discovery, right? And hidden correlation, that's what the correlation is, something very effective in quantum. All right. This is very, very important to note. Quantum computing does not replace AI, it enhances and it accelerates it. All right. So before I move on to the next hybrid AI quantum models, any doubts till now? I want to know whether I'm fast or able to understand. Yes, please. Thank you. Others? Thank you. Any doubts still now? Oh, clear. Thank you so much. Any doubts, you can raise hands and you can ask questions as we move on. All right. So we will move on. So we have started with quantum, and then how what are the major principles of quantum, and where what are the applications of quantum. Then we move on to AI, right? AI, what it does, and what are the limitations of AI. What is the advantage of integrating AI with quantum? All right. So here we go. We work with uh, the hybrid AI quantum models, right? What is AI? So combining your traditional computing and quantum computing in a single learning loop, all right? So it handles data optimization and control, while quantum, it performs computations that are hard, especially if your program is NP hard, right? Of that model, then that's hard for classical machine, and it performs computation that's easier to work. All right. So a classical data processing is what we do. We take a data, we have different packages in Python, and cleaning and what are the different normalization, min max scale or whatever it is, and converted numerical features. And in quantum data encoding, what we do, the classical features are encoded into qubits. I will show you how qubit works, right? Using quantum gates, right? There are different quantum gates available, and like you have worked with logic gates, right? You remember your work with logic gates? Yes, and or XOR, right? They are analogous, but they are operating on qubits. So that's what we call it as quantum gates, right? Quantum gates. So I can show you this. Can you see? These are quantum gates with poly X, poly Y, poly Z. Hadamard gate 1 by, because it takes in all positions, right? Phase SP, pi by 8 is T gate, S gate. C naught is controlled NOT gate. Can you see this is a symbol? If the bits are 4, this is a control NOT gate, control Z gate, swapping, all right, and CC0, CCX, and T of these are like they are analogous to your logic gates, but because each bits take different positions at the same time, because of the superposition principle, these are gates of quantum gates. Whether you're able to see, you're able to see this. These are called quantum gates, right? These are quantum logic gates. I can share the link so that you can find it out. Not able now? You're able to see now? Okay, thank you. So this you need to understand. So I will also show you a model of how to build the simulators of these circuits, right? Right. Maybe I'll show you with Hadamard gate how it works, so you can see the matrix how it works and how it is represented. Oops. All right, so it is zeros and ones, but it can take, because of the superposition around the sphere, it can take both zero, maybe 80% zero, 20% one, and so much and so more. This is the vector representation of a single qubit. All right, this is the vector representation of the single qubit, like zero, because of the superposition. Can you see 1 0, and where 1 is represented by 0 1, the superposition 1 superposition by 0 0 superposition by 1, right? And there are different gates, like identity gate, poly gates, like X, Y, and Z gates, right? And this is how the gates work. Polymatrix works. It's controlled gate, control not gate, C not we say, and you can use it. All right, and this is how, if it is going to be two qubits, 0 0 0 1 1 0 1 1, these are different superpositions that it could take onto that. Maybe at the start it's maybe a little difficult for you to understand. As you journey through, you'll be able to know it, right? And this is one of the Hadamard gate, right? I'll show you a demonstration in today's session how to use this Hadamard gate, and it's named after the French mathematician Hadamard. It's a square matrix of both +1 or -1 whose rows are mutually orthogonal. You can see to it. You can see to it. It's mutually they are orthogonal. All right. So you represent it as H gate, swap gates. The symbol is this, and CC not gate. All right. For you to understand when you create these circuits, right? When you create the circuits. So for circuit creation, you should know what are the gates available, right? Just to, because I know there's a kick start session of this, and most of you are new to this. I do understand. I'm trying to teach you what these gates are. I'm not deep delving into what it works. All right. So classical AI problem, you optimizer is gradient SDG or SGD or different optimizers that you work. Right, error is minimized, but hybrid training loop, it repeats until the model converges. Right, so learning happens through continuous classical quantum interaction. Now, how do you going to develop a quantum circuits as learning components while AI handles optimization and decision making, right? So this is how we are going to work on with. And the first thing is QNNN. I'm just telling you what is what. Maybe if you're interested, maybe you can take up a detailed course so that you can learn and how to develop finding solutions to problem, or how to what do I say, how to write research journals, and so much and so more. All right. Quantum circuit functions like neural network. If you work with deep learning, you know it. Qubit represents the neurons, and quantum gates access weights. I showed you what are the different quantums, right? You know, it works with neurons in the neural networks, right? And when you learn something new, for some of you I would have known before, for some of you I'm new now, you know my name is Doreen. That's a new learning. So it makes a synaptic connection in your brain, right? So same way, through the learning process, the neurons work in your AI models, so an NN, right? Outputs is obtained by measuring qubits. I'll show you a demonstration of how you can have circuits and how you can have the gates and how you can measure it up, right? I will be showing a demonstration of both on IBM and Google on today's session, right? It's very especially useful for non-linear patterning, right? And then the next is variational quantum circuits. That is quantum circuits with trainable parameters. How the parameters are optimized using the classical optimizers we have used. You run the circuit, you measure it, and update the parameters again. Mostly it's used in hybrid model today, and they are the backbone of practical quantum machine learning, right? Variations, quantum circuits. And the third is quantum kernels. Just try to understand what is what. All right. Quantum computers map data into high, I said, right? The dimension of data is limited in classical, but you have a higher dimensional feature space that helps you to converge faster, that helps to find solutions at a faster rate. And similar to kernel methods, like classical methods like support vector machines, or it helps separates complex data efficiently. All right. Then next is quantum reinforcement learning. What is reinforcement? We give a reward, right? We give a reward for something done good. With quantum exploration, that states faster exploration of action space, especially used in logistics, robotics, and network optimization, right? And in real world, millions of drug discovery, if we say millions of possible molecular combinations are taken, right? Each molecule must be evaluated for stability, binding affinity, and energy states. It can do it, but optimization is slow. All right. So, for example, as they find a problem with a patient, and once they have a quantum AI, according to the parameters of the patient, it can give a drug discovery of which are the combinations that would be highly effective to treat the patients for more correctness, right? So, it generates shortlist promising molecular structures, and it simulates molecular energy states more efficiently and interacts at atomic levels, right? And it's faster screening of drug candidates, and then it's better accuracy in comparison with traditional classical AI models, and reduces the cost and time in early stage drug development, right? When you see it from the research side, you can also see from quantum enhanced molecular representation learning, all right, and quantum based molecular embedding. You can also work with molecular property predictions and the stronger scope if you find solutions on IEEE or Springer. I would rather like to show you a recent publication, and just give me a second. Yeah. Can you see the page now? Yeah. Quantum machine assisted drug discovery. Right? You can see when it is published. Today, what's the date? Today we are in 16th, right? Last week this paper got published, right? So now you are able to understand if you want to gear up your research journey, or if a PhD scholars are doing, when you cannot still survive with the traditional AI models, right? Because there is a huge demand in the market, both in the research portfolio of integrating quantum, right? So here you can see this is a paper, right, where the drug discovery is lengthy and expensive with computer aided design. So here we use drug discovery cycle to accelerate rigorous decision making, right? Like molecular simulation, drug target interaction prediction, and optimizing the clinical results. So you can, and this is an open source paper, pipeline of drug discovery. You can see to it like clinically improvement and 1 to 2 candidates, 2 to 5 candidates as the year goes, right? So this is the model that they've developed, right? So from the A, have experimental structure determinations, medical notes, laboratory results, genomic data, and then it goes to 10 power 9 of known versus 10 power 60, and then high throughout screening. It searches through the molecular database, and quantum server navigates a whole molecular space, and then it goes to what is we say it, right, VQE, and then it goes to the excited state energy, and then it moves to the what are the losses calculation. You develop the quantum circuit, find the classical optimizer, and find the low cost, high enrollment, and low enrollment. This is overview of this. All right. If you're interested, I can give you the link of this, and you can just download the paper, and you can get the paper too. right? It's an open source paper, right? If you're interested in doing, you can just search to it and you could get it. All right, and you can read through this paper, and this is a very very good paper, a research article that they have worked with integrating quantum with machine learning for drug discovery. All right, so far so good. Yes. In cybersecurity, if you're going to see, you have lot of attacks. I'll give you a minute or so. Can you search and tell me what are the different cyber attacks, the number of cyber attacks in 2026 or 2025? All right, because we are all into the more than the human world, we are all in the digital world, right? And the threats are so much and so more. You can see in India, all right. See, I'm just showing you statistics. Can you see the estimated cost of cybercrime around the world? Can you see the cost of it? We are in 2026, the 2027, and this is Statistica. They have given this. And all right. And there is very less people to work on with that. And the space is so higher. So they're vulnerable, is very vulnerable to future quantum attacks, detecting complex patterns and real time it is challenging. Once it is integrated, it can analyze the network traffic, whether it is normal or something abnormal, detect what are the different attack patterns. Some of you would have worked with IDS, intrusion detection system, you will know what are the different types of attacks. The quantum optimization speeds up the threat detection and response. The quicker we work, there are different, see, I work by and large lot on cybersecurity. You can know how to create the dashboard, how automatically, it's not only prevention and it's not only detection, we are working with prevention and correction automatically using AI and quantum computing algorithms, right? To search the larger space efficiently, faster and more accurate for intrusion detection and readiness for post quantum security threats. All right. So these are about quantum integrating with hybrid AI. All right. Any questions? Yeah, over 265 million. Thank you. All right. In trading market it works a lot. The future trading market will be working, any algorithm that you're working with prediction will all work with quantum. Yes. Now let me show you the different tools available, right? And this is a package. There are different packages for Python, right? Python libraries for quantum, and one such as CIRQ curve. It's developed by Google. It focused on low level quantum circuit design. I'm going to show you two demonstration, one with Google, the other with one is with IBM. All right, and it's suitable for custom and experimental quantum algorithms. Right, you have different. I can show you. This is from the software. All right, yeah. I've taken CIRQ. Can you see the screen of CIRQ? Yeah. Kirk. All right. It's an open source framework for programming quantum computers. All right. So here you can write, manipulate, and optimize quantum circuits. Remember the gates onto the circuits. It's not the traditional logic gates. It's totally, completely different quantum gates. All right. And running on quantum computers and quantum simulators. And let me show you. And here you've got circuits, you can devices, you have got simulations. I will be showing you how QSIM also works on. All right, for beginners you have got different tutorials that you can also work on with. Mm-hmm. All right, let me go with the demonstration. All right, so first I'm installing pip install CIRQ. There are different Python packages or Python libraries specifically for quantum. Google's quantum AI has given this is like the first step of using it, right? And And after I install, this is the latest version, just as I'm running, I'm installing it. So I'm importing Kirk package and I'm creating two qubits, right? I'm creating two qubits, Q0, Q1, which is equal to Kirk dot line qubit of range 2, because only two, right? I'm having it in Q0 and Q1. So this is the first qubit, Q0 and Q1. You remember, it is not traditional zeros and ones. It can, because of the superposition and entanglement, it keep on changing it, right? So Q0, if I'm going to type Q0, it's CRQ, Kirk dot line qubit of 0. One is line qubit, and you can see what is the data type of it, right? Hope my screen is seen. Right. So here you see it, and this is the two qubits that I've generated using Kirk. All right. I told you about different gates. For example, I'm taking Hadamard gate, H gate, or we say it H gate. So here it's represented like 1 by root 2, 1, 1, 1 minus 1. So if the input is 0 or input is 1, and how you get the output here, creating equal superposition of the two basic states, right? Plus 1 and minus 1, right? So if I want to do that, the same here. See, I'm creating a circuit. First, listen carefully, I'm creating the qubits. The second, I'm creating a circuit using Kirk and applying Hadamard gate. So that is what circuit dot append Kirk dot h off for the q0 qubits, right? The first qubit instance, and I'm appending it, and I'm appending it onto the circuit, the H gate with Q0 onto the circuit, and I'm measuring it. This is a procedure. You create a circuit, you try to give input the different gates with the qubits, and then you measure it, you get your result. So you can see you're starting H and it's measured. Right? You have a circuit, you have a H gate, and you're measuring it, and you're using only the first qubit, Q0, right? This is how the quantum it works, right? This is how it works. All right. And the next is I'm working with the simulator. Simulators is equal to a Kirk dot simulator. Now I'm going to use the what I have created here. I appended onto the circuit. I'm running on the simulator with a repetition of 1,000. You can see the different bits, and each takes different. Each time it takes different, right? So that's what. And next is how do you work with C naught? That's control not gate for 4 bits acting on 2 qubits, right? So this is a matrix representation. It's a circuit representation of C naught gate. All right. And I'm here. I'm going to create an entangled circuit, Kirk dot circuit, and I'm going to append Q naught for H gate. You know, H gate is Hadamard gate, and C naught for entanglement. You know, these two are the principles of quantum computing, Q0 and Q naught. It entangles and keeps on changing, and it could converge fast. And then first I had only H gate. Now I'm integrating H gate with entanglement, H gate for superposition, entanglement for C naught, and I'm getting this. Can you see here? H gate, the C naught, and I'm going to measure it with zero. Here I'm using only zeros with the H gate. For Q1, I'm using the C naught, and I'm measuring both. And this is how I run my entangled circuit and get my results here. All right, just for you to understand, right? I'm showing using Colab and importing Kirk with grid qubit, right? If I'm going to use it with a grid qubit, and how I'm going to work on, and how the simulated results are given. All right. If I want to have a QSIM, right? So for more visualization, then I can use a QSIM, Kirk, and what are the different random rotations with the grid interactions, and you get my, because I've defined here a range of 5, and I'm getting here 5 bits. Can you see? 1, 2, 3, 4, 5. All right. So this is how you can work with Colab in quantum. All right, quantum simulators. Now, taking IBM, right? IBM has got open source framework. All right, it's used for building and running quantum circuits and different simulators. It's used for academic and research. All right, designed for hybrid machine learning for quantum. It integrates PyTorch and TensorFlow. And you remember I told you about variation quantum circuits and QAnon. It works, right? Here it's best AI researchers for entering into quantum computing. For TensorFlow, it works with quantum ML. All right, I'll show you how it works. I will be opening up Quantum Composer. Yeah, I've just already, can you see here? I've got 4 bits. These are the different quantum gates. I've put H gate onto Q0, then C naught, and then on Q2 and C naught, and I'm using T gates. And this is for measuring. This is for measuring. All right, this is my output here. Can you see here? Say, for example, if I remove this, oops. All right, I can have my H gate here, right? Can you see I have my H gate? So I have different, it takes different values. Can you see this is how it takes different values onto this? And then if I'm going to have a NOR gate, and then I'm going to have a T gate, and then I can have C naught, and I can have an H gate here. Can you see as I increase, can you see the differences here? All right, this is Q0, Q1, Q2, and Q3. And then I'm going to have a T gate here. Before having T gate, S is for swap. I'm just showing you a demonstration. I'm trying to have a gate here. But very important is to have the measuring at the end. Sorry. So this is where you get the output. Right? So how do you measure is very important, and then you can see the evaluations around. This is just for an example for you to understand how it works. I've applied had a man, and then you can see how the distribution had a man gate, and then a T gate on H gate, and you can measure. This is how you build your first quantum circuits. All right. Whether you're able to understand till now. All right, you can work with AI for quantum computing, quantum for AI, like interdisciplinary with healthcare, finance, climatical structures, and so much and so more. All right. Any questions till now? Yeah. So let's have a small 5 multiple choice question. I'm putting it onto the chat. The bits of zeros and ones with the different how the qubits or quantum bits work. Right? Just click on the link, give your name, and join. It's 5 multiple choice question. In 2 minutes, I'll just stop it. I can get one. Yeah. Shall I start? And others could join. What is the basic unit of information in quantum computing? We have got 9 people. Others could keep scanning and joining onto the left, or you can give Slido and join. The right answer is qubit, and most of you have given the right answer. First is Ram Kumar, a professor, and I don't know who's hero. You can tell your name. What's the third place is she? Next question. Let's go on. Let's go on to the next question, please. Which quantum property allows a qubit to be in multiple states at the same time? Entanglement, interference, measurement, superposition. 12 of you have joined, others also could join. I can see 12 and 9 of you have answered. And the right answer is superposition. So zeros and ones at the same time. First is Ram Kumar Professor, second is Sam Professor, Sri Ram, Dhanush, and Tanshika. Thank you. Let's move on to the third question for the day. How does quantum computing mainly differs from classical computing? We have come to the third question. There's only two more multiple choice question. Yes, 16 have joined, 11 have answered. Answer fast, answer fast. All right. And the right answer is it processes information probabilistically. Right? Let's see who's on the first place. Professor Ram Kumar, Tanshika, Bhavana, and Samuel, and Sriram. Let's move on to the fourth question for the day. Which problem type is quantum computing especially good at solving? For which? Is it simple arithmetic or text editing or web browsing or complex optimization problems? Quick, please. 3 to 16 have joined. Fast, fast. All right, 14 have answered, and the right answer is complex. So most of you have given the right answer. That's really good. Happy that you're able to understand. Ramkumar, Tanshika, Bhavana, Sam, and Sriram. The final question that will define who's the winner of the day. Quick, please. Which statement is true about quantum computers today? They fully replace classical. They do not require no classical control. They work alongside with classical systems and hybrid models. They are only used for cryptography. 16 of you have joined, 8 have answered, 10 have answered, 11 have answered, 13 answered. Few more to answer. Okay. The writers, they work alongside classical system and hybrid models. And the winner is Bhavana. First place, second place is Tanshika Yogesh. Third place is Dr. Samuel Raj, a crystallite. Fourth is Sriram. And fifth place is Ram Kumar sir. Congratulations. Bhavana, can you unmute? Can you speak? You're from which college? Or let's hear from you, please. Bhavana, you're connected? All right. Or Tanshika or Sam. Oh, yes, please. Congratulations. Like any of the other winners would like to share, what are your three key learnings of the session, please? I- Yeah. Thank you so much. Here we have a blend of people who are very, very new to quantum, and some of them, very few of them, have already worked. So I was trying to blend it. So I've given the link onto the chat. You can type like one line, right? One line of the session. You can give your name, or college name, or organization name, or what is one line about the session on the link that I've given on the chat. All right. You can click the link and give your just one line about the session. And we are planning to have quantum AI course, right? If anybody is interested through this session who have joined, can join. It will be between Jan 24th to Feb 22nd. It will be on every Saturdays and Sundays, especially for students, researchers, and technical professions, especially those who are very new and they want to find solution to problem, or you're working with that. And it will be having a blend of both theory and hands-on. It will be 1 hour session Saturday and Sunday, between 8 to 9. So here we work with AI, with quantum. What is the integration? What is the next bigger research frontier? And what are the different tools and frameworks? And how to gain research, and what are the career directions that you work on with, what are the hands-on exposure. And it's a blend of theory, tools, and real-world insights. and it will be on 24, 25 on Jan, 31st of Jan, 1st February, 7 and 8, 14, 15 and 21 and 22nd we completed. So if you're interested, you can join. So week one, we will be seeing about the quantum and AI foundations of quantum limitations. What is the hybrid system about Kirk? You will be experiencing with your hands on a Kirk and QSIM Kirk. And week two, we speak about QNN, QB, QC, quantum kernels and hybrid models with the simulations. And then the third week, we work with QIS kit, right? Penny Lane and simulators and demo experiments. And fifth, we'll be trying working with you. You have to find a problem, and you'll be working with the literature survey. We'll be guiding you through and what is the research framework. And five, you'll be building a simulator based on the prototype and drafting a research paper outline. All right, this is what it's a blend of both research and finding solutions and to have hands on quantum AI. So general fee structure is 7.5 because those are attending today's session. If you register before Jan 20, you will get 4,999. If you're registering between Jan 20 to Jan 23, you will be getting 5,999. It's only for people who attended this webinars, right? It's very limited seats. If you're really interested, if you want to kickstart, the rate is very, very substantial. And I can say every minute that you work will be more effective. All right. And if you're thank you for attending the seminar. This course we just started because there were so many inquiries that was coming to me to CIRF, and then we started. We can have like 10 hour sessions, right? Like it's like a month course, so it's only on Saturday, Sundays, 1 hour, so that you can have a theory part, your hands-on, and the research perspective. These will be your key takeaways. It's open for students, faculties, researchers, or working professionals whosoever it is, right? So take your next step in your tech journey. So enroll as soon as possible. Don't miss this opportunity. All right. Thank you all for joining the session. I hope the session would have been useful to you. And any questions you can ask. Yes. Mhm. Because the reason behind is in general, in classical computing it's zeros and ones, right? You see if your target, if there is no disease, zero, if it is one. But here the technology or the principle itself is same. It takes zeros and ones simultaneously. So we will not be able to use the traditional models like an AND gate or gate. All right. So, because of the method of superposition and entanglement, there's a different set of gates that you need to use it to build the quantum circuits. Quantum basically works on hardware, and AI works with the software. So, when you're integrating it, when you're working with the qubits, when you develop your circuits, you need gates. For that, we use quantum gates. All right. Well, yes. Codes and circuits say what interrelationally. That's what we'll be teaching you. If you are interested, that's what we'll be teaching you on the course over there. How to- All right. So I'll share you the feedback link. So you can share. So give your names properly so that we'll be able to generate the certificates, and you'll be receiving it by the next week. You're able to get the feedback forms, and is it opening? It will be open for a few, maybe now with the 7/8, it will be there till 7:20, and then it will be closed. Yeah, thank you, madam, ma'am. Everybody, kindly fill your feedback form. For people watching through YouTube Live, you can fill in the form given on the comment. Is the feedback form not opening? I've got six responses. Can you retry, please? Is it opening for others?